Hello Info-Person, this is Anton, and today we're going to discuss a massive leap in our understanding of the universe that doesn't actually involve looking through a typical optical telescope or even using a radio telescope, but instead listening to universe's vibrations using some of the most sophisticated instruments on the planet. And here we're of course talking about gravitational wave interferometry. And though for centuries we were actually limited to observing the universe using telescopes, and specifically observing different wavelengths of light, we have now officially entered a new era where we can hear the universe and discover events we never thought would be possible. The ripples of space-time itself, predicted by Einstein back in 1916. But now, in May of 2026, we officially have another major release, something referred to as GWTC-5, which stands for Gravitational Wave Transient Catalog, that seems to contain some of the richest data yet, providing us with an unprecedented view of the universe, and a universe we never imagined. And so let's discuss some of these recent discoveries in a bit more detail, but I guess just so that we're on the same wave, let's briefly discuss the physics of what we're talking about. So what are gravitational waves? Well, according to Einstein, the entire universe is inside this somewhat foldable and somewhat bendable space-time, a kind of a four-dimensional structure that connects both space and time into a single phenomenon. But massive objects like black holes or neutron stars can actually easily bend it, creating a kind of a space-time fold. And when some of these massive objects start to orbit around each other and form very tight-knit binary systems, their motion creates this. It dynamically stretches and squeezes the space around them, which then sends out waves that travel across the universe at the speed of light. Now technically all orbiting objects produce these, but we can only detect the ones produced by extremely massive objects. And well, to detect this, scientists created a facility referred to as LIGO. That's the one that confirmed their existence in 2015. But ever since then, more and more facilities have now formed a kind of a network, with Virgo in Italy, Kagra in Japan, and LIGO India and GEO 600, essentially creating a kind of an Earth-sized gravitational wave telescope. And all of them rely on the same principle. They essentially use these L-shaped arms that are usually several kilometers long, that then shoot out these very powerful lasers, with the laser light reflected by mirrors at the other end. And if there is some kind of a disturbance in space-time, it actually changes the distance between these mirrors by a tiny distance, something like 10 to the power of minus 18 meters, which then creates a disturbance that's visible in the sensor. And it's actually a ridiculously small distance that's approximately 0.1% of the size of a typical proton. And so these amplitudes are actually extremely tiny and are barely visible. And because it's so ridiculous, Einstein never thought we would find these. Yet, by creating just the right instrument and by doing this over and over, not only have they been now confirmed to exist, as of 2026, as of this new release, we now have nearly 400 official detections. And so it has now become something that happens quite a lot and something that we do observe at least once per week. And so the idea behind this recent study is to kind of summarize all of the main detections, but to also present us with some that are a little bit unusual and some that suggest that the universe is still quite mysterious because some of these collisions are just a little bit strange. Although the primary goal of this study is to now move beyond the analysis of individual candidates and to actually try to combine them into a kind of a statistical analysis in order to understand collective properties of various compact objects, basically black holes and neutron stars. And so the latest update now provides a detail of 161 additional signals detected between April 2024 and the end of January 2025. And that's basically almost daily detection of some kind of a signal, which by itself is already kind of strange because it shows us how extremely common these events turn out to be, even though originally they were predicted to be extremely rare, with the total number of gravitational wave signals now being 390. And because our technology is now getting better and better, a lot of these new signals are much more clear, and in some cases even provide enough evidence to start testing additional propositions and additional physical principles, something we'll discuss in a few minutes. And well, one of the first discoveries out of these 150 mergers is that a lot of black holes are not actually the same. Instead, they seem to fall into three distinct subpopulations. The first group, which makes up about 79% of all detections, usually consists of low-mass black holes, approximately 10 times the mass of the Sun. So that's essentially your stereotypical black hole collision, and these are normally slowly spinning and very stable, and very likely formed through isolated binary evolution, where two large stars are born, and each of them explodes one after another, collapsing into black holes without any outside interference. And over time, they eventually collide. But the second group, that was approximately 15% of detections, seem to be a lot more chaotic. And here, these black holes seem to be much larger at 35 solar masses and also have spins that are often misaligned, which actually suggests that a lot of them were formed in much more crowded environments, possibly in locations like globular clusters, or orbiting the central black hole, where some scientists expect millions of black holes to exist at all times. And so here they're possibly pushed around by other objects, and might even collide with something else before finally creating a final binary collision, with the third group being the rarest. Approximately 2.5% consist of high-mass giants, with some of them containing unequal masses and very complex spin behaviors. And in this case, these black holes seem to be only possible as a result of what's known as hierarchical merger. In other words, these black holes are the children or even grandchildren of much earlier collisions, with this basically being a kind of a second or third generation. And that's actually something that scientists previously believed to be impossible because the universe is just not old enough to create these generations. Yet here, at least 2.5% seem to be that, implying that they must have formed and must exist in some really extreme conditions, once again potentially very close to central black holes. And intriguingly, just a few years ago, we've actually discussed one such event that was extremely strange. This was the event detected in 2023 and involved the most massive collision we've seen so far. Here, the result was a single black hole with a mass of about 225 masses of the Sun, which is actually a bit of a problem for current models. And that's because previously, a lot of physicists assumed that single stars could not directly collapse into black holes of such sizes, and so explaining how this particular black hole formed is actually challenging without these multiple generations. And so this is at least second or possibly third generation black holes merging to create these extremely large giants. With the other notable example being from 2019 that also sort of challenged the classification for such objects. Basically here we had black holes in the so-called mass gap. Black holes that should not have formed from some kind of a supernova or a star collapse and had to have formed in some other way. And so the data from this study seems to directly confirm the existence of these second generation black holes, implying that this is quite common. And on top of this, we also have some of the most precise observations that were actually conducted in 2024. And so here, a signal referred to as GW240615 set the new record for the most precise sky localization amongst all detections to date. And that's because it was actually caught by several different detectors, which then allowed scientists to triangulate its position and localize it to an area of just 6 square degrees in the night skies, a relatively small portion compared to the entire celestial sphere, which obviously then allows scientists to use additional telescopes to actually look at this location and possibly figure out if there is something exploding here or if there is some other unusual event. On top of this, by having so much data now, it's now going to become possible to try to figure out this whole mystery of Hubble tension, or basically the mystery of universe's expansion, and if the expansion seems to follow the so-called Hubble constant, or if there's some kind of a mistake, which will then become visible inside gravitational waves. And that's because by measuring these gravitational waves, it actually allows scientists to estimate the overall distance of these merging objects, which can then be directly compared to visual observations in order to see if there's a discrepancy or if they're basically more or less the same. And since in the past we've actually only used supernova for this, having gravitational waves now provides us additional data. Now there's no conclusive evidence for anything yet, but with 390 points, it will hopefully lead to some conclusions in the future. With the other achievement from all of this being a signal detected in 2025, GW250114. And here this detection was special because it essentially represented the clearest gravitational wave signal detected to date. Here the signal-to-noise ratio is approximately 77 to even 80, even though this was approximately 1.14 billion light-years away from us. And so this allowed scientists to hear an extremely clear overtone coming from the black hole collision, which has previously been completely impossible. And this actually is very important for a lot of additional physical models, because these harmonic vibrations, or this black hole's ring-down phase, when it basically starts to vibrate as a kind of a bell, is a key prediction in many different models, such as the Stephen Hawking's 1971 area theorem, which actually suggests that the total surface area of the final merged black hole has to be always greater than the sum of the surface areas of the two original black holes, which in this case it seems to have actually finally proved. Or in other words, the two black holes, approximately 33 and 32 solar masses in mass, merged into a black hole of 63 solar masses, whose surface area was larger than the surface area of the two progenitors combined, while also confirming a lot of predictions by Einstein and the predictions from the general theory of relativity, all of which have basically been proven by this one single event, with the overall loudness of this hum resulting from this final merged black hole, also confirming that the overall increase in entropy is exactly as predicted in the second law of thermodynamics. Or basically that the laws of thermodynamics also apply to black holes just like other objects. But unlike normal objects, the more energy they have, the colder they become, which I guess is kind of counterintuitive. And that's of course on top of previously discovered extreme events, such as the one from 2019, GW190412, that was also the first ever evidence for a black hole recoil, where the black hole that was merged started to move at 50 km per second, which was fast enough to be ejected entirely from the location where it was formed. All of this essentially visible and observable in these undertones produced by the black hole collision. And so here, by measuring this merger, scientists saw the area of the black holes jump from approximately 240,000 square kilometers to 400,000 after they merged, which proves that black holes obey laws similar to thermodynamics, with the entropy increasing over time. And even more strangely, there is now potentially a discovery of so-called gravitational tails. Or essentially normally, once a black hole merger is over, and following the vibration period referred to as a ring down, some of these new simulations actually suggest that the space-time sort of remains slightly distorted, and essentially this creates these gravitational tails that seem to last for at least some time following the collision, with these tails carrying the evidence of gravity's nonlinearity, or basically meaning that the gravity seems to be able to interact with itself. But obviously exactly how this affects the universe is still uncertain, at least for now. And so overall, in just the last 11 years, the detection of these gravitational waves now provide us with a picture of the universe we actually could never imagine. And that's because unlike light, these waves are not blocked by anything, including gas, and tend to pass through absolutely everything, allowing us to detect them from really far away. And that of course allows us to see the invisible parts of the cosmos, and discover some of these most extreme events that sometimes go completely unnoticed. But we're also in basically early days of this field, because technically it has just begun. With some of the new observations that have been proposed, such as the Einstein telescope, possibly becoming operational in the next 10 years, very likely increasing the detection rate by at least 1,000 times, essentially suggesting that every single day we're going to see at least 1,000 such events. But even within a few years from now, we might be detecting as many as 1,000 mergers per year, even though it was only possible to detect like 5 or 6 10 years ago. And with every new signal here, we're getting a new data point helping us solve mysteries of how the universe began and how its most unusual objects seem to evolve. Which means we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.